Hi everyone, I'm Whit Roy. Today I've invited an electrical tutor and an apprentice to have a conversation as they go through topics from the EWRB Electrician Theory exam. I hope you enjoy this style of learning.
Today we're reviewing topic 12, Systems of Supply. This one's about how electricity is generated, moved around New Zealand, and supplied safely to customers. It's very exam heavy, so we'll take it steady.
Okay, yeah, this is the one with generation and all the high voltages, right? I remember some numbers, but I mixed them up.
That's very normal. Let's start at the beginning. In New Zealand, electricity starts at generation. Most of it comes from hydro, geothermal, wind, and some gas or steam turbines.
The generators don't make super high voltage straight away, do they?
No, they don't. Generation voltage is usually around 11 to 18 kilovolts. That's an important exam figure.
Right, so that's before it goes into the big towers.
Exactly. From there, transformers step the voltage up for transmission. Transmission voltages in New Zealand are typically 110 kilovolts and 220 kilovolts.
Is that just to stop losses over long distances?
Yep, that's the key idea. Higher voltage means lower current for the same power, which reduces heating and losses in the lines.
Okay, that makes sense.
As power gets closer to towns and cities, substations step it back down again. Subtransmission is usually 33 kilovolts, and local distribution is 11 kilovolts.
So 11 kV shows up twice, generation and distribution.
Good spotting. That catches a lot of people out in exams. Then finally, pole-mounted or ground-mounted transformers step it down to customer supply.
That's the 400 and 230 volts, yeah?
Correct. 400 volts phase to phase for three-phase and 230 volts phase to neutral for single-phase.
Most houses are single phase, right?
Most domestic installations are single-phase, yes. Some larger houses or workshops may have three-phase.
And New Zealand uses a four-wire system.
Yes, a three-phase four-wire system. That means 3 active phases and 1 neutral.
So a three-phase customer gets all 3 phases and the neutral.
Exactly. That gives them 400 volts between phases and 230 volts from any phase to neutral.
What about a two-phase customer? I always find that one a bit odd.
Two-phase just means they use any 2 phases. They get 400 volts between those phases, but no neutral connection.
Okay, so single phase is 1 phase and neutral, 2 phase is phase to phase, and 3 phase has everything.
That's a good summary.
Then there's star and delta. I remember the formulas, but not always which way around they go.
That's very common. In a star connection, the line current equals the phase current, and the phase voltage equals the line voltage divided by the square root of 3.
So phase voltage is lower in star.
Correct. That's why star systems commonly give 230 volts phase voltage from a 400 volt supply.
And delta is the opposite.
In delta, the phase voltage equals the line voltage, but the line current is the phase current multiplied by the square root of 3.
So current changes instead of voltage.
Exactly. Exams often test that relationship.
There was also load balancing across the phases.
Yes, balancing the load reduces the neutral current, improves efficiency, and gives more stable voltages. It also reduces stress on transformers and the distribution network.
If it's unbalanced, the neutral current goes up.
That's right. In a balanced star-connected load, the neutral current is 0 because the phase currents cancel out.
But in real life, loads are rarely perfectly balanced.
True. The more unbalanced the phases, the higher the neutral current becomes, which can cause overheating and voltage issues.
Then there was the three-phase power formula.
Yes, power equals the square root of 3 multiplied by voltage, current, and power factor.
That one comes up a lot in exams.
It does, especially for motor loads and cable sizing.
Now the MEN system, that one's really important for safety.
Very important. MEN stands for Multiple Earth Neutral. The neutral is connected to Earth at the distribution transformer and again at the main switchboard through the MEN link.
So that link joins the neutral bar and the earth bar.
Correct. This keeps the neutral close to Earth potential and provides a low resistance path for fault current.
So protective devices can trip quickly.
Exactly. That's the whole safety purpose.
What happens if the MEN link is missing?
That's a critical fault. Exposed metal parts can rise to full phase voltage during a fault, and protective devices may not trip because the fault loop impedance is too high.
So it becomes a serious shock risk.
Yes, and the exam expects you to treat a missing MEN link as extremely dangerous.
Can downstream systems connect to an MEN installation?
They can, as long as the essential MEN features are maintained. There must be only one MEN link, correct earthing, and a fault path that allows rapid disconnection.
Okay, I think that's starting to settle in.
Good. Topic 12 ties together how power is generated, delivered, balanced, and made safe in New Zealand.
Yeah, it's big, but it actually connects a lot of things.
It does. Once this topic clicks, protection and fault topics become much easier.
Thanks, Mark. That was helpful.
No worries at all. We'll keep building on it. Anyway, how's work been lately?
Busy, lots of house rewires, not much motors yet.
That's normal at your stage. Motors will come later. At least the weather's been decent for site work.
Yeah, I can't complain there. Hopefully a quiet weekend to catch up on study.
Sounds like a good plan. Catch you next time.
See ya, thanks.